Hello everybody and welcome to our video on the Cartesian graphs of other trig functions. So we're going to talk about how the process that we use for graphing tangent and cotangent, secant, and cosecant. But before we do that, we're going to talk about another graphing related topic here, and that's the relationship between the tangent function and the slope of a line. So if a non-vertical line makes an angle of theta with the positive x-axis, then the slope m of the line is given by m equals tangent of theta. So this is pretty straightforward. Here we've got this line in purple, and we've got our x-axis here in black. And what we see is wherever this line makes contact with the x-axis and forms an angle theta, that if we just draw a triangle right along that line, then the ratio of the y value to the x value is by definition tangent of theta here. And that is also by definition the slope. It's the rise over the run. So we can use that to give us one more tool for finding equations of lines based on certain information. So let's take a look at this example. Find the slope-intercept form of the equation of the line that passes through the point 2,5 and makes an angle of theta equals 135 degrees with the x-axis. So I want to find the slope of the line, and I know that the slope makes an angle of 135 degrees, and I know that the slope is tangent of that angle. Well, tangent of 135 degrees is sine of 135 degrees divided by cosine of 135 degrees. And maybe I don't remember those off the top of my head, and so I sketch it and I go, okay, that's 135 degrees. That means that my reference angle here is 45 degrees. And so sine is the square root of 2 over 2, and cosine is negative root 2 over 2. And square root of 2 over 2 divided by negative root 2 over 2 is negative 1. So I'll start out by using point-slope form. Now it did ask for slope-intercept form, but I don't know the intercept, so we'll start with point-slope form. That's going to be y minus, and our point is 2, 5, so y minus 5 equals the slope, which is negative 1, times x minus 2. Okay, so y minus 5 equals, and I'll distribute this negative, negative x plus 2. Add the 5 across, and that gives me y equals negative x plus 7. All right, so that'll be our slope-intercept form. Okay, so now we're going to go on to actually finding the Cartesian graph for tangent of x here. And initially this is a little bit more complicated than dealing with sine and cosine, because when we think about tangent of x, we have to think about it as being sine of x divided by cosine of x. So there's a few things, a few key values that we're going to look at for tangent. And then once we understand those key values, then we'll put the whole thing together. So one of the first things I want to talk about is the period for tangent, because that's going to make it a little bit easier to figure out how to graph this thing. So, okay, what's the period for tangent? Well, you might be tempted to say that it's 2 pi, but it's not. And we'll see why that is momentarily when we look at the unit circle. All right, so we're going to consider one point on the unit circle in the first quadrant. This will be theta, and this point will be xy. And then we're going to consider what happens at the angle that's pi plus theta. So I'm just adding pi here. Well, the symmetry of the unit circle tells me that if this point is xy, and I rotate 180 degrees, this point is going to be negative x, negative y. So then what do I see here? I see that tangent of theta, which is equal to y over x, is the same thing as negative y over negative x. I'll move this down here a little bit. But negative y over negative x is the same thing as tangent of theta plus pi. In other words, whenever I add pi to my value of tangent, I'm going to get the same, or to my angle, I'm going to get the same value for my tangent function. So, whereas sine and cosine repeat only every 2 pi, their full pattern of repetition is every 2 pi, tangent repeats every pi. And again, that's because, what do we see? Once we go half of a circle, you start getting these negatives canceling out, and so you end up getting the same values you got in the quadrant that was pi before that. So in other words, that tells me that the period here is pi. So, well, what does that tell me? That tells me that if I can figure out how to graph tangent between 0 and pi, then I should know how to graph tangent everywhere else. So we're going to focus on what's happening between 0 and pi, and just look at how do we analyze this fraction. Well, first of all, let's figure out where is tangent of x undefined, because we've got a fraction here and our denominator can be 0. So we're going to first just take a look at that. Tangent of x is undefined at where? Well, it's wherever cosine of x equals 0. And so which kind of x values do we get? Well, we know cosine of x is 0 at pi over 2. And, you know, we also know it's 0 at negative pi over 2, actually. So we know tangent is undefined at both pi over 2 and negative pi over 2. And since the distance between those is pi, actually, what might make more sense is to focus our graph, which we'll put down here. We'll focus our graph initially between pi over 2 and negative pi over 2. So now my whole distance between these two things is pi, so that's going to cover one period, and then after that we can just repeat whatever we get here. So since this fraction is going to be undefined, that tells me that there's going to be some sort of asymptote here. And, well, that's kind of tricky, right? It's always tricky to evaluate asymptotes. So we know how to deal with that through limits. Let's go ahead and take a look at the limit as x approaches pi over 2 from the left. So when we take the limit as x approaches pi over 2 from the left, what do we get? Well, sine of x is approaching 1, because sine of pi over 2 is 1, but cosine of x is approaching 0. And it's doing so from positive values, because when I say x is approaching pi over 2 from the left, that actually means numbers smaller than pi over 2. So we're actually looking at angles in the first quadrant, and cosine is positive in the first quadrant. So here we have a positive divided by a positive approaching 0, so this limit is infinity. And so from the left here, this thing is going up to infinity. Now, while I'm at it, why don't I take a look at what's happening as x approaches pi over 2 from the right? Well, sine of x is still approaching 1. But cosine of x is approaching 0, this time from negative values. Because we're looking at angles bigger than pi over 2, that puts us in the second quadrant, and we know that cosine is negative in the second quadrant. So this gives us negative infinity. So from the right side of pi over 2, our graph is actually pointing down like that. And since our period is pi here, that tells us that if I go over here to negative pi over 2, this will be pointing down, and this will be pointing up. So now, let's just go ahead and divide this thing into some even pieces. So we've got 0, and then pi over 4, and then negative pi over 4. And let's see what we get here. So I think that'll be the easiest way to finish this up. So we've looked at the most complicated part, what happens when this thing is undefined, what type of asymptotes we get. So let's take a look at tangent of 0. Well, tangent of 0 is sine of 0 divided by cosine of 0, which is 0 divided by 1, which is just 0. So we can just plot that point. And then what happens at tangent of pi over 4? That's sine of pi over 4 divided by cosine of pi over 4. Both of these are the square root of 2 over 2, so when I divide them, I just get 1. And tangent of negative pi over 4, that's sine of negative pi over 4 divided by cosine of negative pi over 4. In this case, sine of negative pi over 4 is negative root 2 over 2, and cosine of negative pi over 4 is positive root 2 over 2. So here I get negative 1. So now if I just connect my dots here and head up towards my asymptote, my graph of tangent looks like this. And the only thing I've got to add in here is that this is going to repeat every pi, right? Every time I add pi, this graph will repeat this pattern. Okay, so that's our graph of tangent. So this is how we figured out all of the key information from tangent. But of course, I just want to point out that when you're actually using the graph of tangent in another problem, you do not want to have to rework through this whole thought process all from scratch. So you really want to commit the basics to memory here. So let me just illustrate that. Here's what you should be able to do pretty quickly and easily whenever you need the graph of tangent. This should be your goal. I look at, okay, I'm going to look at everything from negative pi over 2 to pi over 2. Those are my asymptotes, so you should know, okay, my asymptotes go here. And you should know at pi over 4 and negative pi over 4, those are my other key points. And I'm going to be at 0 at 0, and then 1 here, and negative 1 here, and my graph's going to go up that way and down that way. And then you should just be able to repeat this pattern every pi as much as you need, right? So once you practice this once or twice, this really is a graph that you should be able to draw within a minute, 2 minutes or so. Remember, if you're trying to figure out how to graph a transformation of a function, then the graphing of the original function needs to be really quick, because if you have to spend 10 minutes graphing that function from scratch, then that's going to eat up a lot of time. Whereas if you can do the parent function really quickly, then the transformations will follow quickly as well. Okay, so let's go ahead and move along here and take a look at the graph of secant of x. So we're going to use a similar thought process here for the graph of secant of x, but we actually get a nice little benefit with secant of x, so sort of a trick that allows us to graph secant of x quickly that I'll illustrate once we go through the full thought process here. So first, when we look at secant of x, we should remember that this is really 1 over cosine of x. So we're going to go through the same thought process here. When is secant of x undefined? And that's when cosine of x equals 0. So where is that? Well, cosine of x is 0 at x equals negative pi over 2, at pi over 2, so forth and so on, right? Every pi after that. Now, since the period of cosine is 2 pi, if cosine is repeating its patterns every 2 pi, and this function is just 1 over cosine, the period for secant of x is also 2 pi. So we'll start graphing secant over here, and we'll start by just plotting our asymptotes. So again, we know the function is undefined at pi over 2 and negative pi over 2, because your denominator is approaching 0. And the distance between these asymptotes is pi, and that tells me that every pi I'm going to get another one of those asymptotes. So I'll just draw another one out here. Okay, and what else do I know? I know when cosine of x is equal to 1. That's pretty easy, right? So if cosine of x was equal to 1, so would secant of x. So secant of x equals 1 when cosine of x equals 1. So that's when x equals 0 or 2 pi, so forth and so on, or in the negative direction as well, negative 2 pi, etc. So we'll just plot those 2 points for that. And I know that secant of x equals negative 1 when cosine of x is negative 1, because 1 divided by negative 1 is negative 1. So that would be when x is pi, or negative pi, or 3 pi, right? Any of those. So if we look here at pi, we get negative 1 for secant. And if we look over here at negative pi, we also get negative 1. Okay, now what? Well, I have some asymptotes, and it would be kind of easy to go through each one of these one at a time and evaluate these limits. What's the limit as x approaches pi over 2 from the left? What's the limit as x approaches negative pi over 2 from the right? So forth and so on. But it's actually easy enough to figure out here, because what we know is that at these asymptotes, cosine of x is approaching 0. And we can just look at these quadrants to figure out where is cosine positive. I know that cosine is positive in the fourth quadrant, from negative pi over 2 to 0, and in the first quadrant. And since cosine is positive there, these asymptotes will both be going towards positive infinity. And when I look in the third and fourth quadrant the second and third quadrant, between pi over 2 and pi and 3 pi over 2, cosine is negative in those quadrants, so my asymptotes will be going to negative infinity. And the period for this function is 2 pi, so this thing is just going to repeat its behavior like this every 2 pi. So that's the graph for secant. Now, we can always go through and just analyze this piece by piece, point by point. That's totally fine. But I want to illustrate a very quick way to recreate this thought process with less thinking, right? To make it a little bit more automatic. So here's what we're going to do. We're going to take our graph, and in orange, I'm going to draw the graph for cosine of x. All right, so this is 1. This is negative 1, pi over 2, pi, 3 pi over 2, 2 pi, and back the other direction. So this is how I would expect students typically to go through graphing secant when they need to. Start by graphing cosine really quickly. So that's one you should definitely have down super fast. I look at cosine and go, cosine of 0 is 1, cosine of pi over 2 is 0, cosine of pi is negative 1, then 0, then I get 1, go back the other direction. Connect the dots. Should look like a nice, smooth, continuous curve. And then when you look at this curve, you should say, hey, everywhere that I had a 0 for cosine, when I look at secant of x, which is 1 over cosine of x, everywhere that I had a 0 for secant of x, or for cosine of x, I should get undefined for secant, and I'm going to get an asymptote there. So everywhere you have a 0 for that cosine function, you can just draw an asymptote. And then I know whenever cosine of x is 1, I get 1 for secant. So I'm just going to plot a point at each of these peaks where cosine was 1. And anywhere cosine of x was -1, I get -1 for secant. And so then you can just draw your arrows in the direction of the asymptotes on each side. And so what do we see? We see that the blue graph we get from doing this is the graph for secant of x. So it's just a little bit of a quicker way to reproduce the graph of secant of x, as long as you know your graph of cosine of x really well. You can just trace out cosine of x really quickly, plot all of the peaks and the maximums and minimums, right? And then plot your asymptotes and draw your arrows off towards your asymptotes. So with that one being done, I'm going to leave discovering the graphs of y equals cotangent of x and y equals cosecant of x as an exercise to the viewer. The key thing you should understand is that the process for finding these graphs is exactly the same, but when you go through those graphs, you should be thinking of cotangent as cosine of x divided by sine of x, and think of cosecant of x as 1 divided by sine of x. And then just go through the same process I went through on those two problems, on tangent and secant, and you'll see you're going to get something very similar for these graphs. Okay, so with that being said, we're going to just do one quick example of graphing the function tangent of x over a 1-period interval. Before we dig too much into that, though, let me just add a couple little extra things to think about here that I maybe didn't say explicitly before. So the things I want to talk about are, okay, what are the domain and range of these functions, so that you're thinking about this when you also look at your graphs for cosecant of x and cotangent of x. So notice when we looked at the graph for tangent of x, so the range is -infinity to infinity, right? We can get any output possible for tangent. And the domain, that's a little different. So one of the ways we might denote the domain here is all reals except. So this means like except. So all the real numbers except any of the multiples, any pi over 2, plus any integer multiple of pi, right? So in other words, the domain for tangent is everything except for pi over 2, negative pi over 2, 3 pi over 2, so forth and so on, right? All real numbers except the multiples of pi, pi over 2 plus multiples of pi. And when we look at secant, we see something similar. So the range is a little bit different. So the range actually does not include anything between -1 and 1. So the range is -infinity to -1 inclusive, union with 1 to infinity. And the domain for this thing is the same actually as the domain for tangent of x, because it's all real numbers except for pi over 2 plus any pi multiple. So again, I'll use this notation, real minus any integer multiples of pi plus pi over 2. Okay, so just something to think about when you start to look at cotangent of x and cosecant of x. Okay, so let's graph the function y equals tangent of x minus pi over 4 over a 1-period interval. And so when you do this, I want you to just start out always by quickly graphing the basic graph of the function, the parent graph. And so that's what we're going to do. When I look at tangent, I go, oh, I've got asymptotes at pi over 2 and negative pi over 2. And I'm going to mark pi over 4 on my graph and negative pi over 4. And I get, and I'm going to mark 1 and negative 1 on the y-axis. And then I get 0 in the middle, 1 on the right side, negative 1 on the left side. That shoots up towards the asymptote. And of course, this thing repeats every pi, but the directions say graph it over a 1-period interval. So I'm just going to graph that. So this is y equals tangent of x. And so if I want to shift this to y equals tangent of x minus pi over 4, if I take x minus pi over 4, set it equal to 0, solve it, I get x equals pi over 4. So this is a shift right by pi over 4. So I just take my graph. That should have said pi over 2, not pi over 3. So anywhere I had an asymptote, that should move over. This should also say pi over 4. This is negative pi over 2. That's negative pi over 4. Okay, so my asymptotes should all move over 1, right? Over by pi over 4, but I'm marking every pi over 4. All right, and that one should move from pi over 2 to 3 pi over 4. And so now my 0, instead of being at 0, is going to be at pi over 4. My 1 will be here at pi over 2. And my negative 1 will be at 0. And then my graph looks like that. And that's my graph for y equals tangent of x minus pi over 4. Okay. Well, that's it for this section on the Cartesian graphs of other trig functions. Thank you for watching.